Swayam Prabha. Digital India. Educated India.
O2 gives OH plus O and so on. Okay. Now, once you have decided and once you know this unimolecular, bimolecular and termolecular reactions, and we have said that most of the reactions are bimolecular. Now, how to quantify these rate coefficients? There are many techniques that are involved through experimental measurements, and in particular when you deal with bimolecular reaction and that too in the combustion process, one of the important empirical form of equation that is that essentially governs, and in fact it is simple and becomes highly useful, that is called as Arrhenius equations. Arrhenius is the name of the scientist. He formulated one empirical equations that essentially governs almost all bimolecular reactions, and this will help you to find the or to calculate the rate coefficients. And in fact, it gives, although the typically if you find these rate coefficient reactions, people use molecular collision theory or kinetic theory of gases to find the rate coefficients, but that becomes a very critical part, or maybe not scope of for this course. Rather, we will focus on the calculating the rate coefficient to find out the rate coefficient through Arrhenius form of equations. So, what it says is that A plus B gives C plus D, and we write concentration of dA by dt is equal to minus K bimolecular concentration of A into B, because A and B order is for this reaction order is 2, and this stoichiometric coefficient are also 1 and 1. And what it says is that you define this rate coefficient in a functional form, that is K of which is and he claimed that this rate coefficient is mainly a function of temperatures, and that is expressed as A T to the power B exponential minus E A by R bar T. So, T is the temperature is known, A, B and B are capital A and small b are some empirical parameters, and he introduced E A, which is called as activation energy, and of course, we know R bar is the universal gas constant. So, for example, H plus O2 gives OH plus O. If you talk this, if you use this Arrhenius equations in the temperature range for 300 to 2500 degree Kelvin, we can find out that this A value is this, B is this, B A is 1.2 in 10 to the power 17, B is minus 0.91, E A is 69.1 kilojoule per gram mole. So, this one example when data will be given, temperature is known to us and activation energy one can find out. Activation energy also can be found out from the tabular data. So, the strong advantage for this fact is that we can easily get the rate coefficient through this empirical form, and here we have to use this rate coefficient in a with a unit meter cube per kilomole into second or gram mole into second. Okay. Now, next component that we are going to discuss is the comparison between rate coefficient and equilibrium constant. So, prior to this we have introduced the term equilibrium constant in our previous module, and here we introduce the term rate coefficients. So, let us see what is the resemblance between these two parameters. So, as you have emphasized that measuring rate coefficients of elementary reaction is a very difficult task and it gives lot of uncertainty. So, one way is to find out the equilibrium constants. So, people used to find equilibrium constant like we did whether the mixture is lean or rich through this equilibrium constant, because they are thermodynamic estimates and more precise in many cases, because it is very easy to measure the concentration of species or molar mass or actual mass of the species. By knowing this and try to correlate if there is a link between the equilibrium constant and rate coefficient. By doing so, we find there is a definite link, and that will take as an advantage to correlate these two parameters. So, that is the essential feature of this chemical kinetics. So, and these chemical kinetics equations can be solved at equilibrium, recognizing equal forward and backward reactions. Now, to do this, we consider a case for a forward and reverse reactions in a arbitrary bimolecular situation. We say A plus B gives C plus D, and we can imagine that reaction can proceed as well forward direction and backward directions. Like this again happens in many bimolecular reactions. Reactants concentration of one is a dominant form, sometimes concentration of a C is dominant. So, the reaction can proceed in either directions. To justify this fact, we have to find out what is the in what way the reaction should proceed. So, for example, if, that means like formation of water, we have seen that many intermediate species are formed. Now, when they form, whether those reactions can be in a forward direction or backward directions, that is governed through the rate coefficients. So, for that what you introduce is that while calculating concentration of A with respect to T, we introduced if the reaction has to happen in a forward directions, we say it is a forward rate coefficient Kf, and that is negative. Now, when the reaction has to do in the backward directions, the concentration of C and D becomes dominance. So, we define this rate coefficient as Kr, and it has to be positive. So, at equilibrium both concentration is 0. So, when you look at the equilibrium concentration both equal to 0. So, what we can say that ratio of forward rate coefficient and reverse rate coefficient, which is a function of concentrations number. These concentration numbers can be easily measured, and that number we have already told that is Kc, or we say concentration equilibrium constant based on concentration. Now, same expression we look at in a different way. So, we say Kc is your equilibrium concentration, but when you define this equilibrium constant Kp, it is expressed in the form of partial pressures. So, equilibrium constant, when it is things like there, one way we find the concentration, other way we find this in terms of its partial pressure for each species, concentration for C, D, A and B, and they have raised to the stoichiometric coefficient for their reactions. Now, when I say C and D, I mean they are equal, because when the stoichiometric coefficients are equal, then it takes the form of Kp in this form. So, when I say this, so Kp becomes Kc. So, when the stoichiometric coefficients becomes 1, we say Kc is equal to Kp. So, this gives the information that Kp, if you have a provision to find out the Kp, then we can find out, control the ratio of forward rate coefficient and reverse rate coefficients, and which are mainly function of temperatures. So, the ratio of forward and reverse rate coefficient is equal to equilibrium constant based on the concentration, and the equilibrium constant K p also can be expressed in terms of partial pressures. So, it has been seen that in a bimolecular reactions both are equal, which means it is possible to compute reverse reaction rate from the knowledge of forward rate and the equilibrium constant for the reaction. Conversely, one can calculate the forward rate by knowing the reverse rate. In other words, we can say the chemical kinetic study can provide accurate experimental rate coefficients over a wide range of temperatures. So, this is and these two things will govern rate coefficient and equilibrium constant will govern all the parameters during during all the elementary reactions. So, with this I come to the end of this lecture, but before you leave we will try to solve some numerical problems based on the fundamental concept discussed in this lecture. So, the first problem is based on Fick's law of diffusion. Which says that we have a closed container which consists of CO2 and it is 4 liter capacity and it is sealed with a rubber plug on the top, and this has some thickness of 10 mm and its diameter is 20 mm. So, this is what we say rubber plug. This CO2 is kept at 25 degree and 5 atmosphere pressure. So, 5 atmosphere pressure means very high pressure as well, that means CO2 is in a compressed CO2 has been kept at very high pressures. What the question is that we have to find what is the mass loss. So, here the mass loss is basically the leak that we are going to calculate, and when you say leak you have entire thing CO2 here and rest of the when that means CO2 is going to diffuse into the other medium, and other medium we say if it is air, that means we have need to find out the binary coefficient of CO2 with respect to air. So, if it is going to diffuse, what we are going to what I mean we need to quantify what is the mass loss. So, data that is given is that rho density at rho CO2 that is at 5 atmosphere, it is given 8.9 kg per meter cube. So, let us recall the expressions for rate of mass loss. So, we can say m dot diffusion, that can be written as DAB into area into concentration difference rho A1 minus rho A2 divided by T dx dy by dx. So, here we have to find this the leak through this thickness. So, we can say rho A2 which we can assume to be 0 because it is low concentration, and low concentration and that concentration has to be calculated with respect to air, and rho A1 you can write in terms of density, its density you can write it is very high 9.9 kg per meter cube, and thickness is 10 mm, that is 0.01 meter, diameter 20 mm, that is 0.02 meter. So, and DAB is given that 1.1 into 10 to the power minus 10 meter square per second. And remember, the always the unit of binary diffusion coefficient is meter square per second, because it is a transport properties. Then we can calculate this value like 1.1 into 10 to the power minus 10, area we can say pi by 4 d square, that is 0.02 square, rho A1 it is 8.9 minus 0, thickness is 0.01. So, this number you will calculate, diffusion is very negligible, that is 3 into 10 to the power minus 11 kg per second, hardly there is any leak. Or if you can calculate, that means if you are storing this vessel for years, what is it be effective. So, this number would be about 0.946 into 10 to the power minus 3 kg per year. That means, if you want to calculate this kg, change this kg per second to kg per year, we can say this. Just to give a realistic number, this is about 0.95 grams of per year. So, diffusion of or mass loss from the vessel is almost negligible through this diffusion process, and that also we said, or very rightly, the molecular diffusion process is a very slow process, and this problem demonstrates the same concept. But in some sense, if you want to find the concentration of CO2 and the loss, mass loss, in some situations this maybe if it is a very costly gas or a costly gas like which needs to be carried or needs to be kept for long time, then this loss can be a very vital task. For example, when you carry a liquid oxygen in a satellite to higher altitude or higher space or deep space, so we expect there should not be any loss, because the importance of oxygen is realized as a combustion process during the during combustion process in the deep space, where availability of oxygen is not there. So, in a such scenario, this loss has to be judiciously taken into account. So, next problem we are going to discuss in terms of the rate coefficient versus equilibrium constants. So, we consider a bimolecular reaction, NO plus O gives N plus O2. The rate coefficient in the forward directions is expressed as a function of temperature, and equilibrium constant also is given in the form of Gibbs function. So, we need to find out the reverse rate coefficients. So, the solution of this problem, we have to recall the we have to see that when I say NO plus O gives N plus O2, and we say in the forward directions it is Kf and in the reverse direction it is Kr, that is rate coefficient. What is given is Kf and what is not known is Kr, we need to find out. And but this Kr to be found out, we have to use the Kp, and temperature is given as 23 00 Kelvin. So, the first step that we need to find out what is Kp. So, Kp can be calculated as exp delta G, Gibbs function, molar Gibbs function by R bar T, minus sign is there, and we need data for this Gibbs function calculation. Now, this delta G Gibbs function formation T, we can, for this reaction we can write Gibbs function of formation for nitrogen plus Gibbs function of formation for O2 minus Gibbs function of formation for NO minus Gibbs function of formation for O. Now, here it is a stable gas, this number will be 0 and these 3 data is required. So, you have to take the data from thermodynamics books, and this number I can write as for nitrogen it is 326331 kilojoule per kilomole. For oxygen, for NO, this number is 61243 kilojoule per kilomole. For oxygen, see, you have used this word oxygen for 0 because it is a stable gas. Oxygen is not, atom is not a stable gas. So, we have to find its Gibbs function. This number is 101627 kilojoule per kilomole. So, by inserting this value, and we have R bar is equal to 8.315 kilojoule per kg mole Kelvin. Then by inserting this value, we say delta G Gibbs function change is 163461 kilojoule per kilomole. So, once you know this, we can find, so this will give you Kp by inserting this number is 1.94 into 10 to the power minus 4, and it is unitless. It is unitless because it is the ratio of partial pressures. So, once you have Kp, then we can recall that Kf forward by K reverse, which is a function of temperature, is nothing but Kp, and we are given with K forward reactions, which is a function of temperature, that is 3.8 into 10 to the power 9 T into minus 20820 by T. So, this number by at T is equal to 2300 Kelvin implies Kf T is equal to 1.024 into 10 to the power 9 centimeter cube per gram mole second. So, once you know this, using these equations, this will give you K R, that is reverse reaction. This number would be 5.3 into 10 to the power 12 centimeter cube by gram mole into seconds. So, this expression demonstrates that knowing the equilibrium constant and rate coefficient in the forward directions, one can calculate the rate coefficient for the reverse directions. So, with this I conclude. Thank you for your attention.